Hello everybody, thanks for watching this video. Today I'm going to talk about lattice Boltzmann method applied for the melting and floating of ice. This presentation was presented in the 36th International School of Hydraulics in Poland. So in cold region, ice is common in winter time. Ice is problem. In this video we saw ice floats in river water. So interesting thing is ice induces sediment here, and ice in water involves free surface flow, heat transport, liquid solid phase transition, and fluid solid interactions. To cover all these physical phenomena, we have proposed thermal free surface immersed boundary lattice Boltzmann method. This has generally two modules, namely free surface flow modeling and heat transfer with phase change modeling. We are working on 2D numerical model. Here we see grids and lattices. Each cell in computational domain has indicated by materials such as G for air, IF for free surface, F for fluid, and W for wall or solid surfaces. To model flow, fluid flow, and heat transport, we use double set of distribution functions and use two discretized Boltzmann equations for fluid flow and temperature field. Those two equations are solved on the interface and the fluid cells only. With distribution functions of lattice Boltzmann equation, we can found fluid variables such as density, velocity, and temperatures with those formulae. Then to distinguish the ice and water, and in order to account liquid solid phase transition, we define fluid liquid fraction value that shows water with 1, ice with 0. Two modulus are coupled each other based on some parameters as well as a non-Bosnian approximation for the density division. I want to share a little about the free surface treatment in the lattice Boltzmann method. Free surface is presented by the transformation of interface cells with its mass evolution. On each cell, mass conservation equation is discretized in terms of mesoscopic scale. Free surface lattice Boltzmann method is single phase model, which means air is not considered, and it leaves the free surface boundary condition on interface cells. Generally, boundary conditions in lattice Boltzmann method or lattice Boltzmann method are always given by distribution functions. Floating ice always float on the free surface. Floating ice is a time-dependent, arbitrary shaped floating body. Very interesting thing, shape is arbitrary and it changes over time. So many researchers considered unchangeable arbitrary shaped body for simulation. In addition, physical fields such as temperature distribution inside the ice are often ignored in previous research. So we tried to consider those problems, and for original immersed boundary method, we have inserted our modifications such as submerged volumetric percent and integer center of gravity. In our limited knowledge, we have firstly applied immersed boundary lattice Boltzmann method for a floating body. This is main program of our numerical code in Fortran 77 for fluid solid phase transition in free surface flow. Free surface module is followed by heat transport module where motion of the ice is solved. I would like to show some validation works on the code. This is 1D Stephen problem solving an ice slab melting from the left. Figure on the left, we show temperature distribution and melting fronts in time advance. Numerical, the results of melting fronts show good agreement with the analytical solution. Figures on the right show comparison of temperature profiles at 4 different times at 4 positions. The results by lattice Boltzmann method were in reasonable accuracy with the analytical solution. This was one of the validations for the liquid-solid phase transition. I would like to show a validation for a free surface flow. We conducted Dumbrick experiment and lattice Boltzmann simulations. To check grid independency, we considered two resolutions of the lattice Boltzmann method, and those are the animations in comparison. In figure on the left, we compared the time evolution of waterfront positions by experiment and LBM. Here, fine grid for lattice Boltzmann shows more accurate results. On the right, we show comparison of time evolution of water depth at 2 points. We conclude that lattice Boltzmann method works for a free surface flow very well. I would like to give one more validation for the numerical code. We carried out an experiment of ice cube placed in a glass melting by poured water on it. We measured melting front and remaining ice area and compared the experimental and numerical results. We found also good agreement from the comparison. This is an example of demonstration for melting of motionless ice in free surface flow. We consider weir flow, and ice slab is placed next to the weir. This is numerically defined temperature fields and vector fields with phases at different times. Initial temperature for ice was minus 30, for water 30, and for air 20. Heat transport is shown clearly. On the right, blue is solid phase, ice and free surface, and the vector fields are shown. It took 3.25 minutes to melt ice, and the melting rate was 42 kilogram per minute. Those animations showing phases and the temperature field are created for some time during the simulation. From this kind of simulation, we can find the effect of the velocity and temperature on the melting of ice. This is a demonstration for the freely floating ice. We have performed an experiment and simulation dropping ice cylinder into stagnant water. Measured positions of the ice cylinder are compared in the figure A. Some differences are seen in turning points. They are both likely to be originated from the experiment and numerical work. For example, in experiment, initial flow field or data extracting might be affected, or in the numerical simulation, it depends on what Rayleigh number we use it. For example, we considered here Rayleigh number 10 to the 4. When Rayleigh number is greater than 10 to the 4, the convective flow become more dominant, the inertial flow. Here we see a velocity field on the left and temperature field on the right with the plunging of water and floating of ice. And also we can see temperature distribution because of the ice motion. So in conclusion, we have proposed thermal free surface immersed boundary lattice Boltzmann method for ice problem in free surface flow. This is applicable for other similar problems, but it might be limited for long time and large scale problems. Liquid solid phase transition or ice melting and water freezing can be solved simply, and solution of it is physically very concrete. Numerical code is applicable not only for the arbitrary shaped floating body but also for the immersed body. Lattice Boltzmann method is seemed applicable for all topics of hydraulics, and we are proposing an idea of all-in-one LBM. We saw ice brick video at first, where one interesting thing was sediment induced by ice. It is very interesting to study ice and sediment together. For future improvement, 3D and threadless simulation, multi-body interactions are suggested. And thanks for watching again. Bye bye.